Hello, my name is Robert Shepard, and this is Mycology versus Malaria, the use of fungal natural products to battle malaria-causing Plasmodium falciparum. Plasmodium falciparum is a protozoan parasite that is responsible for the majority of malaria cases in humans. Every year, hundreds of millions of people become infected, and upwards of 500,000 people die from the disease. Unfortunately, the primary victim is young children. With Plasmodium species showing increased resistance to key anti-malarial drugs, including Artemisinin and quinine, it is important that we work to discover new and more effective treatments for this disease. That brings us to my research. The goal of this project was to explore the largely untapped potential of fungal secondary metabolism in hopes of discovering new anti-malarial drug candidates. The first portion of my poster is a simple schematic diagram depicting the transmission of malaria through humans. Essentially, an infected mosquito will pass on infected blood cells to a human. Those blood cells then infect the liver cells, or the Plasmodium species infects the liver cells, and then it produces infected red blood cells that also contain the Plasmodium parasite. Those red blood cells are then contracted by a second mosquito and passed on to another person. This shows the incidence rate or the malaria incidence across the entire globe. As you can see, even though the majority of cases reside in Central and Western Africa, the spread of malaria across the world continues to be a worldwide issue. For this project, we received 80 fungal isolates that were already known to have to be active against malaria. We then performed dereplication and narrowed that list down to just 17 non-cytotoxic isolates, from which we worked with 8. And then the compounds that are talked about in this poster are from this particular fungal culture. On the previous slide, I talked about a process called dereplication. The purpose of dereplication is to recognize and eliminate from consideration active substances that we already have studied in our lab. We do this by comparing the mass data collected from the high-res mass spectrometer, as seen here as the LTQ Orbitrap, and we can compare the high-res mass data from our sample to the high-res mass data of samples that we have previously isolated. And if they contain compounds that we have studied before, we typically don't prioritize those, and we work with something that we have not discovered before. For each filamentous fungi culture, we chop it up and stir it with organic solvent overnight. And then we partition that organic solvent first with water and then with hexane to remove the sugars and fats from our sample. We then send the cleaned up sample for biological testing at the University of Georgia to test for activity against malaria. If they remain active, we then perform a initial separation using flash chromatography, and then we retest those isolated extracts to see if they are still active. If they are, we then take steps to purify them using high performance liquid chromatography. And then once the compounds are pure, we will actually take steps to solve them using high-res mass spectrometry to get the molecular formula for the compounds, and then nuclear magnetic resonance spectroscopy to determine the connectivity of the atoms within those compounds. And that is how we were able to determine the chemical structure of the compounds produced by that one fungus. And that particular fungus produced 8 natural products, as shown here. From those 8, 4 contained high biological activity with IC50 values less than 10 micromolar. And as you can see, this is a chromatogram. Each one of these peaks represents a different compound. And this is from the original fungal growth on rice, on large-scale rice, and it produced these 4 natural products. We then decided to regrow the fungus on 3 different medias on a smaller scale to see if it would change the production of secondary metabolites. What we found is that on rice, Cheerios, and oatmeal, they all produce the same fungal secondary metabolites, except within different amounts. So rice ended up producing the highest amount of extract, producing about 100 milligrams more extract than both the Cheerios and the oatmeal. We also found that on the rice culture, on the small rice culture, it differs actually from the original growth on rice, because we discovered 4 additional natural products being produced by this fungus when we regrew it on a smaller scale. That just goes to show that even changing the size of the growth of a fungus can produce different compounds and different chemistry. I would like to acknowledge the UNCG Office of Undergraduate Research Scholarship and Creativity for providing me with the IRCA grant to help fund this project. I would also like to thank Mycosynthetics and Dr. Kyle for their collaboration and work on this project. And lastly, I would like to thank Christoph Kank, my mentor, as well as all members of the Oberlies research group for mentoring me during this project. Finally, I would like to thank all of you for coming to check out my poster. Please enjoy the rest of the expo. Thank you.